All right, so I'm actually presenting a talk that is not my work. Alex Dimakis, who's the first, who's listed first here, was supposed to be here but couldn't make it. So Alex is my colleague at UT Austin. Sahand is an assistant professor at Yale in statistics, and Ethan Ellenberg and Rajiv Khanna are PhD students at UT. Okay, so this is a story that links together two powerful tools that have been used for for solving high-dimensional statistics problems. And I'll go over both and then tell you the links between them, which is really the contribution of this talk. So the first part, which is going to link to submodularity, is this idea of set function optimization. And set function optimization has to do with finding a subset that maximizes or minimizes some objective. And there's many examples in, now you're getting two mics. There's many examples in large-scale data problems, data summarization, k-medians and k-medioids, and many others. So I think, so here's the k-medioids problem. Basically, given data, the problem is to find a subset of size no more than k that are representative. In this particular case, that minimize the distance to clusters. And these are all examples of hard problems. So in the worst case, these are computationally intractable. So the generic set problem is the following. You have some function f, and you are tasked with finding a subset of your base elements, and there's p of them, here denoted by v, that maximize f. So this is a combinatorial problem in general, and the question that many people have addressed in various settings is, what are the characteristics of f that make this tractable or at least approximable? And submodularity was in the title, so you know what part of the answer is going to be there. So let's turn it back a little bit from the generic combinatorial problem to the statistical question in high-dimensional statistics. So the high-dimensional statistical problem is characterized by having less data than you have degrees of freedom, dimensions. And what makes these problems interesting and what makes them meaningful to write down, I guess many people here are probably experts in this, is that there's some hidden structure. There's some underlying structure that's not linear. And the key example that probably everyone has in mind is some kind of sparsity. And this basically means that you want to do some kind of variable selection. So even though you have p variables, perhaps only some much smaller number of them are non-zero and so are meaningful, but you need to find which ones those are. That's essentially a subset selection problem. And there's many ways, there's many problems and many algorithms that address this. Lasso and sparse PCA are exactly trying to get at this. So these have sparsity in a different way. Lasso has some small number of non-zero variables. Sparse PCA is sparse in its spectrum. And the point is that this allows you to reduce to some lower dimensional structure if you're able to identify this. And this basically gets around this high dimensional statistical issue of having fewer data than at least nominal degrees of freedom. Okay, so the sparse optimization problem is to maximize L of beta. And so I can write this as a set function. So here the set function is going to indicate which are the non-zero variables. So that's exactly what's written. So f of s is the best you can do when you zero out everything that's not an s. Okay, so this is what's written, and canonically you can have in mind that this L is your log likelihood that you want to maximize. Because as I mentioned, generically this is a hard problem. All of the problems that I mentioned have well-known hardness results. Subset cover, k-medians, facility location. These problems span several communities. And we want to understand which structural assumptions can be exploited algorithmically. So again, linking back to the statistical side, we have an answer there. So for the sparse not for facility location, this is for sparse regression, we know what kind of characteristics of our function we need to have. So we need to have some kind of restricted isometry property or restricted eigenvalue property, something that basically says that on all sparse subsets, the objective function has some strict curvature. In fact, that is what this last thing is, restricted strong convexity. Okay, so we know that if these things are present, then we can actually solve these subset selection problems for high dimensional problems. And there's been a huge amount of work studying the statistical aspects of this as well as the algorithmic aspects of this. So on the algorithmic side, people have looked at greedy heuristics, orthogonal matching pursuit, and various adaptations of that. There are various theoretical guarantees that people have obtained using different assumptions, and again, many people, this is just a small subsampling of people that have worked on it. I guess the last few years, especially with a focus towards extending the ideas of sparsity towards low-rank problems, convex optimization has come to the fore, and people have looked at convex relaxations to essentially identify this non-convex structure, to solve these subset selection problems. And these are, and this has been very, very successful. Now, in a parallel development, Das and Kempe, who have used submodularity for many different areas, have turned this and a new definition called weak submodularity, which I'll define in a few slides, to give guarantees, again, for these high-dimensional problems in linear regression. So what this talk is about is trying to connect these two ideas. So to connect concepts like restricted strong convexity, which for the last several years we've had an emerging understanding of how they help us solve these high-dimensional statistical problems, and submodularity. So submodularity is something that basically guarantees that a greedy subset selection method is going to give something that with guaranteed performance. So I don't know how many people here have worked with submodular functions. Actually, Alex didn't know how many people here had worked with submodular functions, so this slide explains. So submodular functions, if you haven't seen them before, it's very easy to give an intuition about them. So again, we're talking about set functions. You choose a set and you get a reward for that set. There's no continuous optimization here. And submodular functions, you can in some way think about them as an analog to concave functions. So what this writes here is diminishing returns. If you think about a concave function, it increases at a slower and slower rate. There's a diminishing return there, and this is exactly what this expresses. So what's written up there, f of a union x, or f of a is the reward you get if you choose subset A. F of a union x is the reward you get if you choose the subset that's A and the union of x. So the left-hand side it's non-negative if f is monotone. Okay, so the right-hand side is what is the additional value, benefit that you get if you add x to your set now if you had b. So diminishing returns says that if I add x to a big set, that increases my value less than if I add x to a subset of that big set. Okay, so that's what's written up there. And monotone again just means that you always benefit. You don't hurt yourself by adding something. So many interesting problems are submodular or monotone submodular. Maximizing log det of a principal submatrix is submodular. This k-medians and k-medioids problem is monotone submodular. Unfortunately, solving GLMs, generalized linear models, is not a submodular problem. So you can't. So logistic regression, linear regression, these things are not submodular. So again, maybe you guys are already all experts in this, so this is kind of an obvious point. But regression is a continuous problem. That's what RT was talking about 2 talks ago. So how am I talking about it as a set function? Again, when I'm talking about it as a set function, I'm thinking about the subset selection, which are the non-zero variables. That's the set that I'm selecting. So what it means that it is not submodular is that you don't have, generally, without further assumptions, have this property of diminishing returns, which means that if I'm solving a sparse regression problem and I have 5 elements on the support and I add a 6th element, that 6th element might give me more benefit in terms of how much my error decreases compared to if I added that 6th element first or if I added it second. Okay, so that's why we don't generically have diminishing returns for these problems. And again, when I'm talking about regression and I'm keep talking about set functions, it's because I'm focused on the problem of finding the subset of non-zero variables. Once that's identified, then I'm just solving the standard regression problem. Okay? Okay, so why is this definition of interest, submodular functions? It's because of this theorem that dates back to 1978 by Nemhauser that says that if your function f is monotone and submodular, then you have a guarantee for the greedy algorithm. So what is the greedy algorithm? You look at the first element, you start with the empty set. The first element you choose is the one that increases f the most, and so on with the second one, and so on with the third. And Nemhauser's result basically says that if your function is monotone and submodular, then you're guaranteed that the set Sk that you build in this sequential greedy way, and of course the benefit of that is that it's computationally very, very simple as long as you can evaluate your function. It's guaranteed to be within a factor of 1 minus 1 over e of the optimal. And it's also known that this can't be improved by polynomial time methods. So for those that are familiar with when roughly we're able to do, or when roughly we're able to solve these sparse regression problems, we know that when would greedy get us in trouble? A greedy algorithm where we're basically choosing rows of our regression, of our covariance matrix, so we're choosing which variables are going to be non-zero, would be very bad if there are rows that are very close to parallel. But if they were all orthogonal, then it's clear that a greedy method would be optimal. So there's something called incoherence, which tries to get at this property that you don't have too many well-aligned columns of your matrix. But it turns out that this is not enough to make linear regression into a submodular problem. So we need to do something. We need to do something more interesting if we want to exploit these tools. So there's this concept called weak submodularity, which essentially relaxes this definition of submodularity, and it goes like this. So let me. This is not too difficult to parse. So if you look at this gamma L comma S, so what's written on the top is how much you gain every time you add one element to your set L. So looking at a set S, so L is, say, elements 1, 2, 3, 4, 5. S is elements 6, 7, 8, 9, 10. The numerator is looking at the cumulative benefit I get by adding each one of the elements 6, 7, 8, 9, 10, one at a time to L. Okay? So let's suppose that F was just how much money you have in your wallet, and you're just adding, and L and S are subsets of different bills. Okay, so what would gamma LS be in that case? F is the money you have in your wallet. See, in this case, it's just additive. Right? So this is actually totally linear. It's not, we have diminishing returns because they're not increasing. But if I have $10 and you give me $5 more, or if I have $100 and you give me $5, in either case, I'm $5 richer. So in this case, gamma LS would be exactly equal to 1. That's called the modular function. So you can check that submodularity is equivalent to asking that, I think this is written somewhere, or maybe in the next slide. A submodularity is exactly asking for gamma LS to be greater than or equal to 1 for all values of L and S. Okay, so this is what we're going to relax. We're basically going to allow values of gamma LS that are less than 1, which weakens the notion of submodularity, and our results are then, Alex's results are then depend on how much less than 1 this gamma is. Okay, so this is the idea. Okay. Yeah, so F is submodular if and only if gamma UK is greater than 1 for all U and K. I was saying gamma LS up there. Gamma UK is just taking a min over S of cardinality K. Okay, so hopping back to the statistical side. So restricted strong concavity and restricted smoothness are properties that are defined and very important in the high-dimensional regime, exactly because if you think about a regression problem in a high-dimensional setting, there are many, many directions. The matrix basically is short and fat for matrix, and so it has a huge null space. Okay, so there are many directions in which case, there are many directions in which there's no curvature to the function. And typically this is what we're after having strong curvature everywhere, also called strong convexity, is the main property that is very useful for proving both statistical error and fast optimization convergence. So a restricted notion of this and of curvature is saying that you only have control in your curvature, upper and lower bounds on your curvature in some select directions. And these select directions, if you're lucky, should match up with the kind of hidden structure that you have in your problem. So, for example, if I want to solve a sparse problem, then I need to have an objective function, a loss function, that has strict curvature, at least in all directions defined by sparse vectors. Okay, so this is what basically this slide says in a more abstract framework. Omega is the set of all is basically the hidden structure you wish to recover. If you had a linear function, this thing in the middle would be 0. And so the term on the right is the upper bound on curvature, called the smoothness, and the term on the left, so little m, is the lower bound on curvature, called the strong convexity parameter. So the main result of Alex, Ahand, Ethan, and Rajiv is that if you have restricted strong convexity and restricted smoothness, this in fact implies weak modularity. So there's a strong connection between, oh, and did I mention before that okay, so this weak submodularity was defined by Das and Kempe. So that's a result, that's a definition that has been around for a while. And they use this to show that for linear regression, if you have, that linear regression is a weakly submodular problem under some assumptions. Okay, so a lot of this work can be seen as putting this into a more properly general, putting that result into a more general context. So the first link here is that if you have restricted strong convexity and restricted smoothness, then that implies that you have weak submodularity. That's what this result says. And that does not imply, but restricted strong convexity does not imply submodularity. So note in particular that little m is the lower bound on curvature in a restricted sense, in the restricted set of directions. Capital M is bigger, so typically this is going to be less than 1. So you're only going to have, you have gamma that's bounded away from 0, but will be typically not equal to 1. So So let's now use this main result to analyze 3 greedy algorithms. So the Oblivious algorithm, what this does is it's essentially a completely non-adaptive algorithm. It says how much would I benefit if I added, what is the value of object 1 in my set? What is the value of object 2? What is the value of object 3 as just single objects? And then it takes the k most it takes the k best ones. This is different than, let's say, what we would naturally think about the greedy algorithm. This is the 3rd bullet point, which is you add the first one, which is going to benefit you the most, and then with that first one already in your pocket, you see which is the second one that would benefit you the most, and so on. Okay, this just says what I just mentioned. It just defines what Oblivious Selection is. So we have the following guarantees for Oblivious Selection. If our loss function, or our likelihood, we're maximizing, it's not a loss. If our likelihood is, or generically any function that we want to maximize, L, is M smooth and M strongly concave on sparse vectors, then this simple greedy algorithm is guaranteed to be within this factor of optimal. Okay, so it's basically little m over big M squared or to the 4th. And k is again the number of elements that you have in your set. So you get this guarantee. Forward stepwise selection is I think what we would naturally think about as a greedy algorithm. And again, I mentioned what this is. So what this says is, in the first step, you take the most valuable element. In the second step, you take the element, you add to it the element that gives you the most valuable 2, and so on. But you can never take something back. You can only add. Okay, and this is superscript G for greedy, and this is the set this is the set. So we get better guarantees here. So in this case, the value of fg is again within a multiplicative factor of the optimal, and you can control it without having to compute gamma, because that might be difficult to compute. But we have this a priori bound, which is given by the restricted strong convexity and smoothness parameters of our function. Orthogonal matching pursuit is a very very natural algorithm that has been extremely well studied for sparse regression. And basically, what it does is it adds the most correlated element, the element that's most correlated to whatever your residual is at all times. So that is what this says. So there are very similar guarantees, slightly weaker than forward greedy selection for the OMP algorithm. And again, I want to point out that all of these algorithms are not just for linear regression; they're for generic functions f. Generic, except that they satisfy little m and capital M restricted strong convexity and restricted smoothness for k-sparse, for the set of k-sparse vectors. So I mentioned that there's no way to improve the approximation ratio that you get from the greedy algorithm for submodular optimization in polynomial time. But there is a way that we can actually get a better objective value, and that's by cheating, which is by adding more values. So before, the 1 minus 1 over e multiplicative factor that you get for submodularity, what that says is that the greedy algorithm, if it selects a set of size k, will be within a factor of 1 minus 1 over e of the optimal case size k set. But you might ask, okay, what if I can choose 2k elements? What can I do then? And indeed, you can do much better. And so these results are well known for, and have been known for a long time for submodularity, but they extend to weak submodularity as well in the following way. So, okay, so now I'm not going to just select R objects. I'm going to select k objects. I'm going to select R, which is more than k. Here it says run algorithm for R steps, because at every step I'm selecting another element of my support. And so so now you can see that we get better values. And in particular, if you're willing to take a constant multiple of k, so this is particularly useful for for problems that are very sparse, then you get an improved approximation. And if you're willing to expand this by a logarithmic fraction, then you get this approximation. So that's it for the main framework and the main results. So let me just show you a few of the results. It looks like they did some experiments on synthetic data, where the sparsity is 50 out of 200. And then they also looked at binary text classification problem, where there are 10,000 samples, about 50,000 dimensions, and the sparsity is 700. And they looked at the forward-backward greedy algorithm. Oh, they compared with 3 additional algorithms. Okay, so what does this show us? So basically what this is showing is that in terms of generalization, the algorithms are doing higher is better in both of these curves. So in the top, what we see lasso is on the bottom. That's not surprising because lasso has this additional term to contend with. But in terms of generalization accuracy, the algorithms are doing fairly well, fairly similarly. But it looks like the greedy selection is on top in both cases. And this is so this is all the synthetic. This is using also logistic regression, and then this is for the text classification problem, where we observe similar trends. Okay, so basically the idea is to link submodularity more closely to tools that we have all been very used to understanding and studying and thinking about for high-dimensional problems, which ultimately boil down to some kind of subset selection problem.
Thanks again for being so brave.